Hello, everyone. My name is Ivan Jain, and this summer I worked with Landry Harimbre and Mark Swizzak and I studied the effects of ion mass-to-charge ratio in plasma for the Kelvin-Helmholtz instability. And so first I want to introduce what the Kelvin-Helmholtz instability is. And so the Kelvin-Helmholtz instability is a hydrodynamic phenomena that exists in many different fluids that is caused by velocity shear. And so here I have a simulation of plasma density for different layers of plasma that are moving at different velocities. And so because of this velocity shear at the interface between these two layers of plasma, we can get the Kelvin-Helmholtz instability. And here in the right, we can see the characteristic Kelvin-Helmholtz waves, as well as we can also see that there are vortices and that will emerge, as well as mixing between in this interface. And so the instability has been observed for plasma as well. And so we know that the instability can occur in many different plasma environments. And so one example is in coronal mass ejections at the surface of the sun or in stars. And so here we have the characteristic Kelvin-Helmholtz waves on the left in this diagram. And we also know that it can occur in decretion disks and jets of active galactic nuclei, or at least we speculate that the Kelvin-Helmholtz instability can occur there, as well as in pulsars. And this is because all you really need is a velocity shear to incite this instability. And so since plasma is consisted of both free electrons as well as ions, we varied the mass-to-charge ratio of the positive ions in our plasma to understand how the dynamics of the Kelvin-Helmholtz waves could change. And so what we've observed is there's particle acceleration that is perpendicular to the initial flow of the plasma in our simulations. And so here to the left, we saw that there was a particle acceleration. And to the right here, we have simulations for different plasma with different mass-to-charge ratios of the ions. And it's important to note that the mass-to-charge ratio of the electrons is 1. And so that's how the numbers here are different from the electron pertaining to the mass-to-charge ratio. And so we know that there's particle acceleration. And so what we examined was how the fields change over time. And so what we found was that there is a generation of the electric field and at the interface between the two different layers of plasma in the x direction. So this is what we believe to have caused the particle acceleration. And we also find that there's a magnetic field generation in the z direction pointing out of the page and into the page. And so we examined if we have conservation of energy of the total system. And so here in the bottom in this plot here, we have a plot of the field energy gain in blue, as well as the total particle energy loss in orange. And we see that they correlate they correlate quite well. So we can say that we do have conservation of energy. And so these are different plots of the magnetic field generation, as well as the electric field energy. And we see that the growth rate of the magnetic fields grows faster and larger for different ions with mass-to-charge ratio. And so future works that we would like to examine is if there's an actual saturation of this self-generated magnetic field. And so I played the simulation for t equals 1,000. And what I found was that it seems that the growth seems to slow down, but it still hasn't reached an equilibrium. And we also see that the electric field grows as well. And we would like to understand if there is an equilibrium that the system reaches at very large timescales. And we would also like to vary the mass-to-charge ratio for the positive ions more and see if there's a threshold by which we don't see this phenomena occur. Thank you. If you have any questions, I'll be at my poster labeled K.